Hello everyone, my name is Jeff Bulmer, and today I'm going to be discussing our paper FASTT, Team Formation Using Fair Division. Now last time I went through this and tried to record this, I realized there is quite a lot to cover, so I'm going to ask that you please leave your questions until the end, but we will get there. So I'm going to probably go pretty quick, so I'm just going to get started. So first I'm going to start by talking about our motivation for this. Then I'll touch briefly on the the two main areas that we want to get into, team formation problem and fair allocation. Then I'll talk about the fair allocation of several teams to tasks. That is our problem setting. I will briefly touch on the multiple round robin algorithm, which is our algorithm. Hopefully I will have enough time to do that. Then I'm going to talk about our experimental evaluation, and then I'll touch talk about the implications of this work and future work that could be done. So here's our motivation. Why are we doing this? Let's imagine a project-based course consisting of several students that need to be assigned to teams for group projects. Many of you have probably done this, this year even. I'm sure that this is a pretty regular thing for a lot of you. So the idea is, how do we create these teams? Should we do it randomly? Should we let the students decide? Should we let the professor decide? What's the best way to create these? More importantly, is there a way that we could divide up the groups in such a way as to guarantee the best possible results for each project and also ensure that each student is happy with their group? So in this case, we would need to consider the requirements of each project, the skills of each student, any existing relationships between students, who likes each other, who hates each other, who works well together, and we would also need to make sure that all students are assigned to a group at the end, because we don't want anyone getting left out just because they didn't fit in it as well as they could have in some group. So I'm going to step back for a moment and talk very briefly about the areas that we're going to be employing here. The first one is team formation. The goal of team formation is to assign several students to one project. I'm going to use our nomenclature here and ensure that all project requirements are met. In particular, from team formation, we look at a paper by Lapas et al. Called Finding a Team of Experts in a Social Network. That is the most relevant to us. They consider student skills and project requirements as well as all underlying student relationships as a social network graph. Their algorithms aim to cover all project requirements, so make sure every project requirement is met by the skills of the people in the group, while also minimizing communication costs. So essentially keeping people that like each other together, keeping people that don't like each other apart, or work well together, however you want to define that. In summary, they consider one project and its requirements, they consider several students and their skills, and they consider the existing relationships between students. The biggest problem is that they only consider one project, so we need to consider multiple. The one possible solution is maybe we could use one instance of team formation per project, but if we do that, we can no longer guarantee full coverage for each project, because what if all projects need one skill that only one student has, for example. The other area we look at is fair allocation, where we try to assign several items, which are usually objects or like treasure, something like that, to several agents, which are usually people, in a fair way. Each agent expresses some value over each item, and the fairness is then based off of these values. There's a bunch of different fairness criteria that you can look at. Of particular interest to us is envy-freeness, which says that the resulting so two agents are envy-free with respect to each other if they couldn't switch their items and get a better total value out of that result. And then the whole allocation is envy-free if every agent is envy-free with respect to every other agent. So that it may not be immediately obvious why we would want to apply fair allocation to the team formation problem, but it works really well in our setting. In particular, if we consider each project as an agent and each student as an item, which you could think of as, say, like each project is represented by a team lead who picks students for the group. If we do that, now we can apply fair allocation techniques to assign students to projects. And the advantage of that is that there are many efficient algorithms to calculate complete allocations. So that means allocations where every item is assigned to an agent. In our case, every student is on a team. And fairness notions are just generally very well suited to our group work setting. For example, if we run into the situation where some project can't be fully covered, then we can at least ensure that every project has an equal chance as every other project to get completed. So our setting our problem that we came up with is called the fair allocation of several teams to tasks. And so what we do is we combine elements of team formation with techniques from fair allocation. So one instance of our problem is composed of the following. We have a set of projects, each with a set of requirements. We've got a set of students, each of whom has a set of skills. And then we have a graph representing the underlying social network of these students. A low edge weight between two students means that they would work well together. And a high edge weight, conversely, means they wouldn't. Additionally, some other definitions. We've got XI is the team of students assigned to a project I. CI is the coverage of a project I, which is defined as the number of requirements that are met by students in XI. We've got the formal definition right there in the footnote if you want to take a look at that. Then we also need to define the communication cost. I touched on this briefly earlier. The specific way we're going to formally define communication cost is the diameter, which is the longest, shortest path between any two nodes, so any two students in a team. In particular, so this would essentially represent the two students that are going to work least well together. The diameter would be representative of that. Okay, finally, we need our value function. I will talk about our specific value function later, briefly, or soon. But in general, the value function is going to be a two-parameter function where xi, where m is the student that's going to be assigned, and xi is the team of students that are currently assigned. Because we're using a two-parameter function, that means that the value of each student for any project may change whenever a student is assigned. But we can more easily consider communication cost and coverage by just building these into that value function. So to summarize very quickly, our goal is going to be to find a team for each project we want to find teams for each project so that the resulting allocation meets the following conditions. As many requirements of every project as possible are met by the skills of the students assigned to that project. And the communication cost is as low as possible for each team. And of course, all students need to be assigned to a project. So to do that, we're going to define our value function with coverage and communication cost built in. So the value of each student m to a project I is going to be comprised of the number of yet unmet requirements fulfilled by that student, so the number of extra skills that that student brings to the project that are actually required by the project, and the communication cost of adding that student to the team. So if there's the change in diameter based on adding that student. The total value of a team is then given by the number of requirements met by all students in that team minus the diameter of that team. So I touched briefly earlier on envy-freeness and envy-freeness, or I touched briefly earlier on envy-freeness. There's also a relaxation of envy-freeness called envy-freeness up to one item, which is if you could achieve envy-freeness between two agents, any two agents, by just removing at most one item from the combined set of all of their stuff, from the combined set of both teams, then you have envy-freeness up to one item. In our setting, just to sort of alleviate confusion when dealing with people, we call these complete balance up to order and complete balance up to order in one item, respectively. These are essentially the same as envy-freeness and envy-freeness up to one item. We just call them complete balance up to order and complete balance up to order in one item. So complete balance up to order, real quick, this is the idea of that. I have already described envy-freeness, so I'm just going to leave this here and I won't really go into it too much. But the important thing to note here is that envy-freeness is notoriously difficult to achieve in many cases, which extends obviously to complete balance up to order. So we relax it to complete balance up to order and one item, which has its definition right there. Okay, so now I'm going to talk about the algorithm we came up with, which is the multiple round-robin algorithm. So our solution algorithm is modeled on fair allocation techniques, specifically the double round-robin from a paper by Harris-Aziz et al. And here's the idea, is that we're going to perform a series of truncated selection rounds which proceed as follows. So we iterate through all the projects, starting with the lowest valued team and going to the highest valued team. And then each project either selects the highest valued available student or adds a dummy student if there is no remaining student that has a positive value. As soon as one student has been assigned, then we reevaluate entirely. We recalculate all of the student values because they may have changed. Then we find the least valued, the project with the lowest valued team, and we do this whole thing again. Once everyone's assigned, we have an adjust winners algorithm check to make sure that the resulting allocation is CBO1, and it'll attempt to balance it further by swapping students to try and fix any of those errors. I'm going to show you these algorithms. I'm not going to dwell on them too long because I do have limited time. But yeah, so this is our multiple round-robin algorithm, which hopefully you should be able to go back and pause on this. We also obviously have this in the paper. This is our adjust winners algorithm, which is of course part of the multiple round-robin algorithm. And real briefly, I wanted to bring up that unfortunately this algorithm does not guarantee, it doesn't provably result in a CBO1 allocation for every problem instance, just because the adjust winners algorithm may introduce additional errors on teams that it's not. In trying to fix CBO1 errors between two teams, it may accidentally result in CBO1 errors between two other teams, and we have to stop it before it loops endlessly on that. So unfortunately, it doesn't provably result in a CBO1 allocation for every problem instance, but we can normally achieve that goal, and we will show that in the next section, and it works pretty well. The runtime is stated there. It's mostly due to the these for loops in here. Anyway. Okay, so our data set, we used a benchmark data set created from a snapshot of the DBLP bibliography server taken on July 1st, 2019. We processed it in the same way as Lapas et al. In the paper that I had mentioned earlier for easy comparison. I won't go into too many of the specifics of how we set up each of our, of how we process that, but it is all mentioned in the paper. Essentially, these are all of our students are actually computer science authors who have skills taken from the keywords in their papers. So we tested our algorithm, and we also used the double round robin from Aziz and the generalized envy graph algorithm from Aziz et al. As well. And we reported our performance based on the average running time to find an allocation on over 500 trials, the average resulting team coverage over 500 trials, and the number of CB01 allocations found in those trials. So I'm going to show the graphs. Here we go. So the first thing is the average elapsed time versus the number of students. As the number of students increases, the complexity of all of these algorithms increases as well. You can see that the MRR, which is our algorithm, is in almost every case it's the fastest, except for right around this 10, this sort of 7 to 10 area. DRR is always pretty competitive with it. The algorithms are quite similar. The generalized envy graph algorithm works quite differently and can actually get stuck sometimes. I think that may be what happened around 17 here, where it just can't continue. But either way, it takes much longer. The standard, so this is the CB01 count. Our algorithm found a CB01 allocation in almost every instance. As you can see at the top, that is not a straight line at 100, so it did fluctuate between about 100% and 98% CB01 allocations found. The generalized envy graph algorithm wasn't able to do that, and the DRR algorithm actually performed similarly well to MRR most of the time. There's a dip around 8, though. And the average project coverage. So the average project coverage, this is how many of the requirements of a project were met by the skills of a student, or of all the students assigned to it. MRR usually does best, but only very rarely achieves anywhere close to 100. DRR is also doing pretty well, and the GEG algorithm is not doing very well at all. So our results and our implications here. So our work, so what we did find is, I just want to touch real quick, what we did find is that just by changing that value function, some of the existing fair allocation algorithms already work very well in our setting, DRR specifically, although that just changing that value function doesn't necessarily result in perfect results, because in every algorithm, because the generalized envy graph obviously does not do very well in any of these. Yeah, so our work paves the way for future work in both fair allocation and multi-project team formation. In particular, we actually defined a setting in fair allocation that is powerful enough to account for order, although our value function, we deliberately kept it order agnostic. And we also generalized the team formation problem to allow for multiple teams to be formed without sacrificing the benefits of single team formation. In the future, we are actually already testing an improved version of our algorithms on real courses to see that if we can get this to work in a practical setting. And future work could also consider other fairness concepts such as proportionality, envy-freeness up to the least valued good, things like that. I am out of time, so at this point I would like to take questions. I hope it will be available for me to do in the chat. And yeah, please let me know if you have any questions.